That's going to be a duo presentation by Andrea Pilla, who's working for Schuko International as innovation and product development engineer, as well as Pedro Villarino, working for Sika. Gentlemen, the stage is yours.
Thank you. Thank you very much. So today we will present together this innovation that we are working on. It has been for a while, so we are happy to share a few updates on this. So I will start from the basis, from when all of this came from, and I'm from Schuko, so we produce a facade. We realize profile for facade, and like most of the unitized facade nowadays, it's not always the case, but most of these for out-of-plane loads are designed in such a way from a structural point of view that the wind load, so the out-of-plane load, is taken directly, fully by the aluminium. Then you design most of the time the glass as an infill panel. And whenever you design a SG, so structurally glazed unitized facade, you combine the two and you calculate the structural silicon, of course, to transfer some of the loads. But it's very rare in large fabrication of unitized facade, SG unitized facade, to consider any partial composite action due to the interaction between the aluminium and the insulating glass unit. So, of course, there are many typical sections. You can do sections of a unitized SG facade in many, many ways. This is like, for example, an example of a cross-section for a unitized SG facade. So an external IGU, most of the time insulate the double glaze unit. And then you have the main mullion that, as I said, is designed to carry fully the out-of-plane loads. And then sometimes you have an adaptive profile, a carrier frame for easy or replacement. So the aim of the study it's mainly two big aims. The first one, it's a bit easier. So we want to challenge the conventional structural hierarchy of a structurally glazed unitized facade. So we want finally to push the market to consider in most of the project, whole the project, the partial composite behavior between the glass and aluminium, thanks to given by the bonding of the structural silicon. But we also want to do a further step, because this is sometimes in challenging project already done. So we want to further enhance that partially composite action. And why we want to enhance that? To optimize the material usage. So we want to reduce the quantity of aluminium that we use in our facades. Therefore, in this way, we can lower the facade carbon emissions. Of course, we want to leave the same glass that we will use in a traditional unit. And of course, we will improve the aesthetical quality of the unitized facade. So when we look at the beam and we talk about partial composite behavior, I'm pretty sure that most of you are familiar with this. The way we are designing facade most of the time nowadays, it's case A. So we assume that the out-of-plane load is applied on this case of a beam, but the concept is the same, on a naked beam, so only on the aluminium. In reality, we are fabricating units that are, so we could already calculate it nowadays, case scenario C, where we have the glass and aluminium, again, that they are working partially in a composite way due to the structural silicon. And then we have case E, that will be a theoretically fully rigid bonding connection. That is, again, a theoretical, but is not absolutely ideal case scenario. So that will be possible if we had a material connecting glass and aluminium that will have rigid stiffness similar to the one of the materials. But this, of course, will create problems, because we know that glass and aluminium have two different thermal expansion coefficients. So we will create high stresses in this connection, and we will create also the bowing of the unit. So what the technology and the innovation that we develop is what we call it minimal wall. So it consists on introducing a dual sealant system in which we have in the central part still normal structural silicon, and at the edges of the beam, and of course when you think of a unit, at the edges of at the corners of a unit, are increased rigidity adhesive. And we put it at the corners because, of course, that is the area where we have the highest shear transfer. So where putting something more rigid will create the biggest effect in reduction of the deflection. And here at the bottom you can see the curve, how going farther, like we can further reduce for the same external load, the out-of-plane deflection, the mid-span deflection, analyzing more and more as a partial composite behavior beam. So, of course, this was the theory. Then we said, OK, let's start doing some real tests. We started from some beam tests to see if the concept was valid, and also to start investigating different materials, different of these rigid adhesive that we could use. And we did around 40 different samples. We used 7 different adhesive configurations. You will see soon, because we played also with the length of this rigid material at the ends of the beam. And all these tests were done in-house in our technology center. And here you can see a reduced version of the samples we did, because, as I said, we tested different materials. So here I focus on the profile on the samples with the secondary adhesive that at the end we selected. And what you can see, we did the first test, that was the test number 1, that was like the lower baseline, just aluminum beam. Then we did the second test with the full structural silicon, currently available on the market from Sika. And then we did the test number 4 and 6, the series number 4 and 6, with structural silicon SG500 from Sika at the center, and then at the edges we put Sika Force 930 that Pedro will talk more about this material, and it's a polyurethane. And we put for 2 different lengths, so you will see soon. So length, so for 250 millimeters both sides, and 450 millimeters on both sides. And then just for an experiment, a theoretical study, we did also some beams with these secondary adhesive on the full length. But this was purely for a scientific study, not for real application. So we performed a long series of 4-point bending tests, so to measure the deflection of these beams. And we tested all the beams for L over 200, that is the traditional serviceability limit state, deflection limit for facades. And then we tested up so we recorded tests up to L over 60. That can be considered a sort of ultimate limit state in terms of, let's say, deflection. These are just to give a representation of the tests we performed. So the beams were around 3 meters long, and with a glass panel of 600 millimeter width that represent more or less the influence area of a unit that is 3.3 by 1.5 meter wide. And in order to focus the study fully on the bonding itself, we remove all the pollution that could be around. So we didn't put any carrier frame. We just used a pure rectangular section, anodized. We put a glass that was a monolithic glass, non-laminated glass, just again not to have the influence of the PVB on the deflection. And we put the joint, the structural silicon joint and the adhesive joint, exactly in the center of the configuration. And as I said, we use different lengths, so sometimes 225, and then we combine the two. In some other samples, we use 450. And these are the results that you can see here. These are again only of the selected samples, and these are average results of all the samples we did. Of course, for each series, for statistical reason, we did more than one test. And the black line at the bottom represents again the lower baseline, so the naked beam in aluminum. And then you can see series number 2, the SG500 on the full length. And in the best case scenario, with this dual sealant system, that is combination series number 6, we can achieve for a deflection at the deflection of 15 millimeter. So for the serviceability limit, an increase on the force apply in order to achieve the same deflection of the 91%. So it's a huge increase of force that you need to apply in order to achieve exactly the same deflection at midspan with the different configuration. What is important for us, polyurethane, it's a new material. It's not codified, the use of polyurethane in facades. We know that, and we need to do something that can be also applicable in the next like in the next years in the market. So what we want to do is to propose a new design concept in which we say that from a ultimate limit state for safety check of these units, we don't want to change anything as it is currently from, let's say, the way we check the structural silicon. So we will use only the structural silicon that is, let's say, in the rest of the panels to verify for safety our units. This means that practically, when we will calculate in our finite element model the units, we will leave some gaps at the corners. Where we want to take advantage of the polyurethane, it's only at the serviceability limit state. So it means only for deflection checks. And at that point, with a full material characterization and full material study, we are confident that we can easily justify that it's just for deflection, and we can take into account the beneficial effect of the polyurethane.
So we need to find a product that is strength enough to fulfill the requirements from Schuko, but also that is rigid enough to gain this functionality with a composite action. But we need to keep certain elasticity for the expected thermal dilatation movements on the joints. And I found this, we have a nice product, Sika Force 930L15 in Sika, that could fulfill this specification. So when we are using an adhesive, or we plan to use an adhesive, we need to evaluate their mechanics under different conditions, because the adhesive may be affected by the service temperatures, the load cycles, duration of the load, exposure, egging condition, applied joint thickness, plus also surface treatments and substrate. So we need to consider all these topics to really develop a correct design of the joint and to select the proper adhesive for the application. So we start the experimental procedure with Schuko, and we need to test not only the mechanical performance and the properties of the adhesive, but also the properties of the joint. Schuko system has fixed joint dimensions, 19 millimeter by 6 millimeter, and then we evaluate the tensile and the shear properties of the joint. Then here you have a picture of the specimens, tensile H specimens, standard with the specific joint dimensions as in the standards are the same as in the standards, and then I create a new specimen to be able to test also the shear properties on the joint. Then we also carry out the standard test. So this is really dog bone or dumbbell specimens to evaluate the tensile properties at different temperatures. We really need to do sensibility study to see how the different temperatures are affecting the properties of the material. We use the same specimens to evaluate or to calculate the Poisson ratio. This is really necessary for the FEM analysis. So this is a value that we need to know. We use these specimens also to evaluate the effect of artificial aging. So we subject the material to really hard conditions to see or to evaluate where are the limits of the adhesive. And here is basically the test that we subjected the adhesive. So we evaluate after each one, but we only take after all of them. So we are comparing the material when it's cure with the material after all the egging process. In addition, we evaluate the fatigue performance according to the ETAC. So if we are using or we want to use in a facade, so we need to ensure that also is able to fulfill the requirements in the ETAC, or the majority of them. And finally, compatibility. So we need to check that the compatibility between the Sika 4930 L15 and the silicon, the Sika Seal G500, is good. It means that the silicon is not affected by the polyurethane, and the polyurethane is not affected by the silicon. And we have an internal procedure, as you can see. So we have 2 glass panes with 2 adhesive sheets. We subject the system to 6 weeks at 70 degrees, and then we check the mechanical performance, and it cannot vary, basically. And then we prove that it's also working. So here we are starting with the results part. So here are the tensile properties out of 8 specimens. It's the specimens that I showed you before. So you see that the material is quite stable below 55 degrees and until -40, and we have a drop at 80 degrees. This is somehow expected. The good point is that even under with this drop, the requirements of Schuko and the system is still fulfilling. But for us, it's really important that the material is quite stable in a long range of temperature. Then for the CR test, we see a similar behavior. So we have the drop, the blue line is 80 degrees, logic with the temperature. And then also a good point is that the low temperature is not making heavily rigid the adhesive. This is quite good because of the thermal topic, thermal dilatation and so on. Then here I show the results out of the tensile test, the dog bone or dumbbell specimens. So -20 is more rigid, but then is what we expect basically. So this stiffness is decreasing, but again the good point is that we are really between the limits of the system. So it's really performing as it should do. Here I show the Poisson ratio at different temperatures. It's quite stable with the temperatures, both the engineering value and the true value. And we use this information for the sensibility analysis to really evaluate the performance of the system. Artificial aging. So what is really interesting is that the tensile strength after all these steps that I showed you before is still in the same level, plus 3%. We have a drop in the rigidity as expected. So, but really into the limits that we need to fulfill, and the material is a bit more elastic. So even after egging, we see that the performance against the thermal dilatation will be even better. Here, the fatigue performance of the product. So we are really, really happy with that because the lab shear strength is a drop of 5%. That is basically standard deviations. You are really on the same level. All of the samples survive. So and we use the same fatigue cycles as in the ETAC. And then finally, here the compatibility. So we prove also that the Sika 4930 is fully compatible with the silicon. That was really good. So the silicon is not affecting the polyurethane, and the polyurethane is not affecting the silicon. So they can work together in this technology. And then, as conclusions, so it's really important to understand what are the mechanical performance and properties of the adhesive if we want to really do the proper structural analysis of the technology, of this technology. And then we need to know not only the mechanical performance, but also the fatigue performance and the compatibility. And then we evaluate the compatibility with the silicon, but also with the other elements of the system. And then with this test, we validate, and also with the help of an external office, engineering office, we validate that the system works. And this is really good because also proof that this adhesive, this technology is useful and is valid for advanced facade designs. And then in the future, we are now working on approvals and on a full escape test that will come, and maybe in the next GPD conference we can show the final results of this technology. And now, if there is any question, so we are happy to answer. Yes.